Hello everyone, my name is Malinta Fernando and today I'm presenting CoCo Games, Graphical Game-Theoretic Swarm Control for Communication-Aware Coverage. This work was published in IEEE Robotics and Automation Letters. My co-authors are Dr. Ransalu Senanayaga from the Machine Learning Group of Stanford University and Professor Martin Swani from the Open Network Group of Indiana University. Now, what is multi-robot coverage? Multi-robot coverage generally involves distributing a robot team over a region of interest to maximize some kind of an objective function. That objective function can include maximizing an information gain or providing mobile wireless coverage. The application areas include space exploration, rescue operations, and environmental monitoring. Especially in next generation 5G and 6G networks, UAV robots with wireless routers can act as an interim layer between the smart devices and the base stations. The idea is to improve the connectivity with more mobility and ubiquity. However, when the ground robots are operating over large geographic regions to perform their tasks, uncertainties in wireless communication can cause multiple problems, such as they can fail to scale over the geographic region or in the number of robots, they can fail to adhere to centralized control commands, or even under decentralized control that can prevent them from aggregating the global swarm state, causing problems in the decision-making system. Here we present some simulation results of a network robot swarm navigating over a region of interest with wireless signal attenuation. From the left-hand side plot, we can see that the expected received signal strength, or RSS, or the performance measure of this work drops significantly as the robots move further away from each other. And as a result, from the right-hand side plot, we can see that the number of communication hops between the robots increases, and finally, the system becomes completely disconnected. One approach is to use mobile and wireless networks. Here we consider a scenario with a group of ground user equipment robots shown in purple color and a UAV robot team. The UAV robots are equipped with wireless routers and they need to position themselves to enable the communication among the ground robot nodes by acting as a backbone network. The user equipment robots can move arbitrarily in the environment to perform their tasks. They can connect to the UAV router with the highest received signal strength. So our objective is to coordinate the UAV swarm in a decentralized manner to maximize the received signal strength of the ground robots nodes as they move. However, the problem is, as the ground robots navigate over the terrain due to the communication limitations, UAV robots may risk losing the connectivity and not being able to scale with the ground robots. So in this research, we asked the question, can we unify network-level routing information with robot dynamics to develop robust, scalable, and dynamically feasible decision-making frameworks under stochastic communication? In this work, we assume the stochasticity in communication derives from this wireless signal attenuation and the time-varying nature of the communication topology. So we present CoCo games, or communication-aware cooperative coverage games. CoCo games is a decentralized control approach for the UAV swarm to make their control decisions by leveraging network-level routing information. To do this, we first construct a mesh communication topology over the entire UAV swarm. This allows the robots to dynamically populate their routing tables by taking the link breakages into account. Then each robot identifies its neighbors using the local routing information and a pre-specified number of communication hops. For example, the black robot here has 3 neighbors at a single hop communication distance. Next, we decompose the centralized game into a series of local graphical games. We propose 3 ways of doing that. 1. Each UAV can construct local games by observing the states of its single hop neighbors. 2. Each UAV may increase the hop count to aggregate the states from its higher order neighbors. 3. Each UAV may construct local games with virtual neighbors that represent the states of its higher order neighbors. For example, the purple color robot may aggregate the states of the red and the blue color robots, and then the green color robot may aggregate the states of the green and the yellow color robots. In this work, we rely on the assumption that each robot's utility only depends on its local neighbors' states. So, from a game theoretic point of view, the best action of a robot only depends on the neighborhood. This is a great simplification from the conventional stochastic games where each robot's action must depend on the entire swarm. First, we have to identify the region of interest that we need to cover. We can do that by calculating a theme abstraction based on the ground robot distribution. We can do so by using a Gaussian distribution. Next, each UAV partitions this space by the number of neighbors using a communication model. For example, here the red robot has 2 neighbors. It identifies the areas within the region of interest that each neighbor can cover the best and partitions it accordingly. Using this partitioning, we define a utility function to map the UAV's actions into total received signal strength. The utility function combines the signal strengths each neighbor can impart on the region of interest as a unary factor, psi c, and the inter-UAV signal strength as a pairwise factor, or psi r. The objective here is to find a consensus action profile for the neighborhood by each robot, optimizing this utility function independently. Basically, we synthesize each local game into a Markov random field and find the posterior distribution over this Markov random field. In this work, we use mean field variational inference to solve the local games. In our paper, we show the posterior distribution resembles with the mixed strategy Nash equilibrium for the neighborhood. We evaluated our approach in stationary and moving ground robot scenarios using 3 and 8 UAV nodes. The ground robots here are shown as blue dots. We can see as the robots spread over the region of interest, the communication links among them changes over time. However, they manage to reach the consensus. Also, as they spread, the received signal strength of the ground robots increase. We use third-order neighborhoods to compute the actions for the UAV robots in both the stationary and moving scenarios. We compare the results to using fixed radii neighborhood models, and there is a clear increase in the consensus received signal strength in routing information-based neighborhoods. And also, as the number of UAVs increases, we can see a clear increase in the received signal strength of the robots as well. On the computational front, our approach always stays at a manageable 25 milliseconds for the optimization loop, even for large geographic regions. That means we could coordinate the robots in real time. For the experiments, we use a 10 meter by 10 meter discretization, which means each cell here represents an area of 100 square meters. In conclusion, CoCo Games unifies the network level routing information with their dynamical models to coordinate the robots operating over large geographic regions under uncertain communication. In an ongoing work, we extend this approach by learning different robot interaction models and communication models. The take-home message: CoCo games are a simplified way to solve multiplayer general sum games using their interaction models. CoCo games can also solve a graphical game as a probabilistic inference problem. My name is Malinda Fernando, and if you're interested, you can download our paper from this QR code. And thank you so much for listening.